Our first speaker is going to be Winn Darden. He's a business manager for Lumaflon, a fluoropolymer resin for the Americas.
We're going to talk about, or try to talk a little bit about long-life bridge coating systems. And we'll do an overview of top coats, bridge top coats in general, and fluorinated top coats in particular. Go through some weatherability and corrosion resistance information, run through a couple of specifications, a short life cycle analysis, and then a couple of case studies on the materials. So conventional coatings, most people think of a three-coat system when they're painting a bridge: a zinc primer, epoxy middle coat, and a polyurethane top coat. These do offer good corrosion protection, but the top coat can start to change in appearance and start chalking and fading relatively quickly. Fluoropolymer coating systems use the same three coats. There's nothing changed about the primer and the middle coat. These FEVE, or fluoroethylene vinyl ether materials, were developed in the early 1980s. And these products withstand UV exposure for 2 to 3 times the length of conventional coating resins. And we'll demonstrate that through some weatherability and corrosion resistance. Just a brief on polymer structure. We call this FEVE because it's a fluoroethylene vinyl ether copolymer. Just like polyethylene is used in plastic bags, you just name it after what you react with to get it. And what you've got here are alternating structures of a fluorinated unit with a vinyl ether. The fluorinated unit is what gives the weatherability and corrosion resistance. The vinyl ether allows us to put functional groups on it to make it soluble in solvents and to make it reactive. So most people who are using these materials are making fluorinated polyurethanes. The chemistry is no different than a polyurethane chemistry. The life of the material, though, is much longer. These have excellent weatherability. You can expect a 30-plus year top coat life from these materials. Very good gloss and color retention, good corrosion resistance, resistance to chalking. Because these are soluble in solvents, you can use these both in shop application and in field application, so for new construction and for existing bridges. These products, by using the right resin, you can formulate these to meet all air quality regulations, including South Coast, which is 100 grams per liter or less. These have good chemical resistance, and they are resistant to cleaning solvents, so you can make anti-graffiti coatings with these products if you want to. Talk a little bit about weathering. In the paint industry, we use two types. One is accelerated, the other is real-time. Accelerated weathering, all of the methods suffer from some default or defect, but they're good for screening and comparing the performance of coatings. Real-time weathering are areas like we put panels, coated panels out in places like South Florida for 20 years or more. Well, obviously that's not practical if you're going to sell a product, so usually most people use a combination of real-time and accelerated weathering tests. This is a typical chart that we see for accelerated weathering. This one is called QUV-B. The coatings are exposed to one wavelength of light at 313 nanometers. And we use gloss retention as a proxy for performance. So the higher the gloss retention, that is, the flatter that line is, the better the gloss retention and the better the durability of the coating. And you can see they've compared the, this to a standard polyurethane, and this isn't, oh well, that's all right. Anyway, Imakwa testing is a little bit different. What they're doing is they're focusing all wavelengths of light onto a coating using mirrors. There's a wet and dry cycle with this test, and they're getting the same type of results. You can see, again, the better the gloss retention, the better the performance of the coating or the long-term durability of the coating. This is real-time weathering, so all we're doing here is putting this out in South Florida. The panels are put at a certain angle to the sun. You let them sit out there, and you know, every 6 months or every year you go out and read the gloss retention. And you can see the good gloss retention of 80% that these have after 10 years in South Florida. These resins, FEVE resins, are manufactured in Japan. They use Okinawa as their Florida. And this is Okinawa weathering for 12 years. And again, it's comparing two different types of fluoropolymer resins that they're looking at here, FEVE and PVDF. This is a test on an offshore platform in a bay that's south of Tokyo Bay in Japan. And what they'll do on this platform is they have decks on it, and they'll test metals, new alloys, and coatings on this so they can expose, for example, you get tidal exposure as the tide moves up and down. You can put pieces of metal on the legs of the platform and see what the corrosion resistance is for being immersed in salt water and then being above the water as the tide goes in and out. What they're measuring here is they're measuring the loss of coating thickness over a 13 to 16 year period. What they're showing here is that the polyurethane material, basically that 1 mil or 25 microns, is gone after 13 years. The FEVE coating of that original 1 mil, about 21 microns, which is about 85% of the coating thickness, still remains after 16 years of exposure, which is pretty remarkable. You're really looking at erosion by rain and wind and things like that when you start to talk those type of numbers. This is a chalking test on the same platform. 10 is considered to be good. If you're down at 0, the panel is completely chalked. And you can see how rapidly the polyurethane, the red line, does start to go down. After about 4 years, you're already getting a lot of chalking on the coating. And all chalking is the polymer degrading and breaking into small bits that can then be washed away with wind and rain, and that's how coatings degrade. If you walk up to your house after 5 or 6 years, you can wipe your fingers on it and you'll see paint on your hands. It's the same thing happening here. Most people are putting coatings on bridges for corrosion resistance. The primary driver of corrosion resistance is really the zinc primer. It corrodes preferentially to steel if the coating is damaged. The top coat serves to block corrosion initiators like oxygen, water, and chloride. Because fluorinated materials have lower degradation rates, that means they're going to be around longer to help keep these materials out of from reaching the zinc primer. So that's the main advantage to these. Sorry, Marco Rubio did that on TV, and I did it here. Oh no. This is a cyclic Prohesion test, and basically what you're really looking at over here is you're looking at the maximum creep, and I think there's an AASHTO standard that requires an 8 millimeter maximum creep, and you can see the fluorourethane does have good maximum creep and good corrosion resistance. The real differences come when you're looking at the gloss retention over a period of time. These are also exposed to in a weatherometer to some form of ultraviolet light. And the same thing over here. You're just looking at a different zinc-rich primer over here and a different polyamide epoxy over here. And again, you can see the difference in the gloss retention, and you can see the urethane and the fluorourethane offer about the same corrosion resistance. So a lot of the performance in this test is really driven by the primer that you pick. It's not necessarily driven by the top coat. This is ASTM B117, just visual. I don't have any blistering information on it, but you can see visually that the FEVE coating does seem to have better corrosion resistance than the polysiloxane does. Just visual again. Same thing here with the polyurethane, and the same thing you can see there. Again, this is the salt fog test after 3,000 hours, and this is just in table form basically. And a 5 is considered excellent results, and then 3 is average. It goes all the way down to 1. I think it may even go to 0. But so you can see all of these different systems have adequate corrosion protection. The fluorourethane does appear to outperform the other coating types in this test. We also run electrochemical impedance spectroscopy. You're setting up a corrosion cell with a coating on one side and a salt solution on the other. And basically, as the chloride, water, and oxygen move through the film, you set up a new corrosion cells, and you're really measuring the difference in impedance between those. And in this particular test, to top everything off, what they've done is they've put it in the SWOM, which is an accelerated weathering test. So again, what they've done, they've measured impedance at various points along the way. And again, the flatter the line, the less change in impedance, the better the protection the coating is going to offer against corrosion. There are a number of bridge top coat specifications with this. These products have been used in Japan for close to 30 years now, maybe even 35 years. And the standard you're looking at here is the 1995 specification for bridge top coats. And what you can see is they define different environments. They define the environment, and then they specify the types of coatings that can go in there. And at the time this was done, they were still using alkyds, they were using chlorinated rubbers, they used polyurethanes, silicone alkyds, and you can see then that they recommend only for the worst environments the fluoropolymer coating system. Now by 2005, this has changed. Basically what they're recommending now is regardless of the environment, they're recommending the fluoropolymer top coats on the coating system. So most of the bridges in Japan that are being repainted today and are being built today are going to be coated with a fluorinated top coat. And again, it's going to be a similar three-coat type of system with a zinc primer, epoxy, and then a fluorourethane top coat. And you can see here, this is a shop application product, and this is a repair or for field application. And they have slightly different application techniques and slightly different requirements. You might formulate the coating for field application to be brush applied in certain cases. So you'd have to reformulate somewhat in there. This is a specification from the Iowa Department of Transportation. They're building a new bridge over the Mississippi River in the Quad Cities area up in northeast Iowa. And what they've done here is you can see they're specifying the fluorourethane as a top coat. What they've done, they've modified their existing polyurethane specification to include the fluorinated material. And if you go to this page, you can also find a list of people who are considered to be qualified suppliers of coatings to the Iowa DOT. There's a steel structures coating specification by the International Standards Organization, or ISO 12944. These standards are really more used in Europe than they're used over here, but they're starting to get an audience over here. They've recently updated this. It's updated this year. And what they've done here is they've added a section to the polyurethane section where they describe the fluoropolymer materials, and then they say that these will be more durable than the polyurethane coatings. My understanding is they're trying to revise it again to kind of break out the more durable materials so that they can have a category of their own rather than being categorized with standard coatings like that. So this is a kind of a rough life cycle cost analysis, basically looking at top coat thickness, and then what's the coating cost in dollars per square meter. So we looked at an alkyd, a polyurethane, and then a fluorourethane. And when you look at the cost, the alkyd's $1.50, the polyurethane's about $4. Well, the fluorourethane can be 5 to 6 times the price of the polyurethane in dollars per gallon. And when you apply it on that, when you only consider the cost of the coating. But that's not the real truth here. The real truth is that the paint application and the paint itself, the cost of that is usually less than 10% of the total cost of coating a bridge. So to bump up the quality of the coating that you're using, or the coating system that you're using, doesn't make that much of a difference in the overall performance of or the overall cost of applying the coating. Most of your dollars are going to be spent in other areas like surface preparation, rigging and containment, travel, and things like that. That's where your costs lie, not very much with the application of the coating or the cost of the coating. And this is basically then looking at those three coatings and looking at the total repainting cost. And when you start to look at that at dollars per meter or square meter, what you start to see is, well, all of a sudden now the overall cost, yeah, the fluorourethane's higher cost, but it's only about 25% higher now, or 22% higher than the standard polyurethane. The other thing to consider is, what is the estimated coating life that you're getting out of this? And the real metric that really needs to be applied to a paint system on a bridge, just like the bridge itself, you own that paint. If you're a DOT and you're painting a bridge, you own the bridge and you own the paint. And what you're looking at here is that you're really looking at what is the total cost in dollars per square meter per year. That's what it costs you to own that coating. And this is when you can really start to see the advantages of the FEVE or the fluorourethane material. And you can see you're anywhere from 25% less than a polyurethane on that basis to almost 33%, actually 67% less than the polyurethane, depending on the life that you assign to it. And in one case here, you got 30 years, the other case, you've got 60 years. And there are bridges in Japan that are painted with these materials that the expected life of the bridge is 100 years, and they want to repaint it one time during the life of the bridge. So they're very serious about using these high-quality materials to reduce the maintenance costs. Just real briefly, this is some 30-year exposure data. What you really want to look at here is the delta E of 3.5. The change in color is very small for a red. I could probably not see that visually with my eyes. And then again, look at the gloss retention here, and after you wipe the dirt and everything off, it's 97% after 30 years. This is another bridge, again, same type of area. Up in the mountains, they use a lot of road salt. There's no chalking. You can see they put stripe coats down in the areas where they need it. And again, what you're looking at here is after 30 years, you're looking at gloss retention of about 74%. So that's remarkable for a bridge coating, especially in a red, to retain gloss that long. And this is a list of bridges in the U.S. That have been top coated with the fluoropolymer materials. And these, the latest one is the Navy Pier pedestrian bridge in Chicago. That's right along the lakefront over there. So based on accelerated and real-time testing, these fluoropolymer top coats have very good weathering and corrosion resistance. Life of these coatings can be expected to be 30 to 60 years. They can be shop or field applied. Good life cycle cost advantages, and there's environmental advantages to using these as well.
30 to 60, the large variation, how do you get to that?
A lot of it's going to depend on the environment. So if you're in for example, a seacoast environment, you'd probably be at the lower end of that scale. If you're in an inland environment, I would, in the U.S., you might say like Dallas, Texas, right? Well, you know, UV exposure is pretty high in Dallas, but they don't use road salt. So, you know, if it snows or gets icy in Dallas, they throw sand on it. So in an area like that, you can expect to get that longer lifespan. But if you're on a bridge over the intercoastal waterway or something over here, you're probably looking at 30 in that case.
Is there any special procedures for repair?
I think it's just going to be standard techniques that you would use to repair a coating. So you'd want to abrade the surface to some extent. You might consider using a primer depending on how far down you are. If you go down to bare metal, for example, you might want to put a zinc primer down to repair it as well. And the advantage of this, of course, is you're not going to get the measles on a red bridge. You're not going to see a lot of different spots with different colors because the color retention and gloss retention is so good with these. So the appearance of the bridge ought to remain good for longer periods of time. Thank you, guys. I appreciate your time.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.